Okay, there's going okay. Back here. Okay. Okay, this should be working now. So this should, everything, I think, work hunky-dory. We'll see how it actually turns out. But I put a lot of time into actually being able to do this again, so if it doesn't, I will feel very sad. A couple things here before we move on. Number one, this weekend is about the Jubilee Lake excursion, which is very interesting and fun, and you should really consider going. Even if you're not a member of Biology Club, it's only $5 for non-members, and that includes like food and things, and then you canoe on Jubilee Lake, which is fun. You don't have to worry because Jubilee Lake at its deepest point is only like 12 feet deep. So even if you fall in,
you can never die.
Yeah, there is that. Anyhow, die, yeah, that, yeah. You would, everywhere. But you can't say you would never die because there have been people who drowned in Jubilee Lake in Columbia water. Yeah, that's depressing. Okay, all that being aside, do consider going to this because this is fun and interesting and it's a good time, and Jubilee Lake is a pretty place, and especially in the fall, right now as it's getting colder, and some of the larches start turning purple. I mean, purple? What in the world? Yellow? I don't, okay, never mind. I'll just go on and I'll talk about cell biology. I do that better. Okay, we have been talking about enzymes, and before we talk much more about enzymes and how they work, we need to take a pause here for a moment and talk about thermodynamics. And thermodynamics really is just the study of how energy changes during physical processes. Particularly here, we're talking about chemical reactions. And so that's really what's underlying thermodynamics. Again, originally this was used to describe heat instead of just all energy, but we now know it applies to all energy. And dynamics is just kind of talking about change, like things are dynamic or things that change and morph over time. So we're really talking about changing energy and how does that work. And so there's really there's several different laws of thermodynamics, but the ones that we are interested here talking about are the first two. I'm going to go over those really quick. They should be somewhat familiar to you. But the first law being you can neither create nor destroy energy. Now that being said, it can be transformed. You can take heat and turn it into light turn it into heat. You can get mechanical energy and turn it into chemical energy and vice versa. You can change the kind of energy you have. And other extreme cases, you can actually transfer between energy and matter, but that's well beyond what we're talking about with enzymes. So we cannot create or destroy energy, but it can be transformed. Which leads to one particularly important and interesting measure of energy in a system. That's the total energy. The total energy in a system isn't going, or not to change. And that, in the case of biological systems anyways, is enthalpy. And we use the term H to describe enthalpy. Enthalpy, at least as far as we're talking in biological systems, is the total energy of that system. So that is the first law of thermodynamics. The second law, then, is that every event proceeds in such a way that it increases the universal randomness or disorder. And this is what we call entropy. In other words, every reaction or every process that happens is going to increase the total entropy of the system. And the entropy we abbreviate using the term S. Now this has the consequence that this means that all chemical reactions, no chemical reactions, are ever 100% efficient. because you have to increase the entropy of the system when this happens. This is because some of the energy from every reaction is going to go into increasing the entropy, and therefore that energy is not available to do work. So the difference between this now is what's known as the free energy. We have the total energy of a system, and anytime we undergo a reaction, then we're going to, some of that energy has to go towards increasing the entropy. And what is left then is the energy that is available to do work, that we can actually accomplish things with. And that is known as the free energy, which we abbreviate with G. Another way to put these first two laws that we talked about now is that if every process is going to increase the entropy, that means every process occurs will have to decrease the free energy. Because again, there's no good way in a closed system to increase or decrease the total energy. We can't create or destroy energy. So if this changes, if the entropy increases, then this has to go down. The free energy has to decrease. So all processes that occur spontaneously without adding more enthalpy, adding more energy to the system, have to decrease the free energy of the system. Or in other words, have a negative delta G. Delta G being the change in the free energy, all of those processes have to have a negative delta G. Now we can get around that if we increase the total energy of the system, but that's kind of beside what we're talking about here. So, the change, or the delta G now, another way that we can put this is the free energy in the products minus the free energy in the reactants. How much energy do we have in the end of a chemical process minus how much do we have at the beginning? And that is the change that occurred in the free energy. Therefore, if, as it should be, the G is less in the products than the reactants, which all spontaneous reactions, that should be the case. It should decrease the free energy because our entropy had to raise. Then this should be negative. Another way of writing this is that delta G equals the change in the enthalpy minus the change in the entropy. And the change in the entropy is, in this case, multiplied by the temperature because that is temperature dependent. Where we just look at this again in relationship to this, delta G equals this minus this. Really is this equation restated over again, but just slightly changed, and that the change in each of those then is H minus the enthalpy minus the entropy is the free energy. Okay, so let's take a look at this. In reality, here is how the delta G of any given reaction is actually determined. And you don't need to know this exact equation, but I want you to know, if you saw this, what the consequences are of this. So the delta G is equal to the delta G naught, I'm going to talk about what that is, times a couple constants, which are the 2.303, R is another constant, times the temperature, and the log base 10 of the concentration of the products over the concentration of the reactants. There's a couple things here that I want to draw your particular attention to. The first one is, what is this delta G odd here? This is the standard free energy of a reaction. If we had a reaction in very standard conditions, what is the change in the free energy if that reaction were to occur? R is a constant here that we use to calculate this. It's not important that you know this exactly, but just for your references. 8.315 joules per Kelvin per mole. So essentially this energy per temperature, degree temperature, per mole, which is per concentration of the reactants and the products. And again, T is just temperature in Kelvin. So the actual change in free energy is going to be influenced by the temperature that the reaction occurs at. So the temperature is going to change that. And also the concentration of the products and the reactants. Those also have influence over how, or the change in free energy that we see in reaction. Therefore, all positive reactions that have a positive delta G are an endergonic reaction. This means that we need an input of energy. They will not happen spontaneously. You need to input energy to the system to get them to work. Because we can't create or destroy energy. If you need more energy at the end than you had at the beginning after you account for the increase in entropy, you have to get that from somewhere. It doesn't just come out of nowhere. On the other hand, if it has a negative, if a reaction has a negative delta G, it is an exergonic reaction. And this means that this occurs spontaneously. This can occur spontaneously. It doesn't necessarily, but it can occur spontaneously without an outside input of energy. It means that also we are going to release that free energy over the course of this. So that free energy has to go somewhere. Oftentimes it releases heat. Not always, but oftentimes that's going to be released as heat. So, with that in place, we can begin to talk a little bit more about actually how do these reactions proceed and how fast they will happen, and that is kinetics. Kinetics is determining how quickly or how rapidly a reaction is going to proceed. So, let me just remind you real fast about kind of the basic model of how enzymes work. So, over here, at the beginning, we have the product, or excuse me, the reactants. We have an enzyme, and we have its substrate. And in kind of traditional nomenclature of chemical reactions, these would be the reactants. And then we have this in the middle. This is the enzyme substrate complex, or in this case would be what's known as a transition state. And at the end we have the enzyme releasing the products. This would be just the products of the reaction. So let's look at how this would proceed then, kind of graphing out the free energy of this. If we look at the reaction over time, we have this as we go into the reaction. This is the free energy of the reactants. At the very end, we have the free energy or the G of the products. And as you can see, this would be a spontaneous reaction because we have a lower G of the products than the reactants, which means if we subtract the G of the products from the G of the reactants, we'd have a negative number. We have a drop in free energy. Does that make sense? Now, a lot of reactions, however, have to go through a transition state. It's not just an automatic, you go from the G of the products to the G of the reactants. There's a transition state that actually has a higher free energy than the G of the reactants. And the difference between this, the difference between the free energy of the reactants and then the free energy of the transition state is known as the delta G hatch, or the activation energy. This is the free energy that is required for the transition state. You can't proceed from here, you can't proceed from up here, can't proceed from up here to down here without first getting over this hump and down. The change from here to here, the change from the reactants to the products, is known as we've talked about before, just the delta G of the whole reaction. Okay, so how would this happen? How would we get from the delta G of the, or the G of the reactants to the G of the products over the transition state? Well, if we think about the energy that molecules have, they're not all exactly at the same energy. There's a distribution. There's usually a normal distribution around some mean. So if we look at the number of molecules in some group of molecules and the free energy that they have, they might be at some certain temperature, have some average total energy, but there's going to be tails on either side of that. Some of those, some in the tail here, will actually be greater than that energy of activation already. So even if, as we see here, the reactants on average have this free energy, they won't all exactly have that free energy. There'll be a distribution. Most of them will have that, but we'll have some down here that have a lot less free energy. We'll have some up here that have a lot more free energy. And those ones that are up here above that free energy will be able to trickle over this transition state and go down to here. Does that make sense? So some molecules will be able to kind of get over the hump and get there, just because we have this distribution of free energies within a system. So let's think about this for a second. How can we increase the speed that this reaction happens? How can we increase the number of molecules that can get over this hump? Wow, there's a lot of things.
Lower the activation energy.
You can lower the activation energy. Anything else? Add more free energy. Yeah. Those are both very good. So adding more free energy could include adding heat to it. So we could add more free energy by heating up the reactants. And essentially what we do is we do this. We move the mean, or move this distribution up as we add more heat to reaction, and you get a bigger proportion of the molecules that are above that threshold. More of the molecules will be over the threshold, and they'll start dumping over, and you can increase the speed of that reaction. And as was also said, the other way that you can make this happen quickly is to do this: lower that activation energy. We can lower the threshold at which they need to get over from here down to here, so a greater number of those molecules actually have that energy, and we can proceed more quickly over that hump. So essentially we can move this up or move this transition state down. Biology prefers one of these ways. It really doesn't like to boil your innards, heating you up. Now, occasionally that does work. There's a reason that you get like a fever and stuff like that. There are occasions where warming up your enzyme or warming up your biological molecules is a good idea. There's a lot of exothermic animals that heat up their insides to get things to work faster. But in general, you can only do that within a certain range. You cannot, as we were talking about before, with carbonic anhydrase, we increase the reaction rate of going between carbonic acid and carbon dioxide by like 1,000,000-fold. we can't do that by heating you up. We would heat you up so much that all of your other biological molecules would start breaking. And so, the preferred way to do this, the preferred way to increase the rate of reactions in biological systems is to reduce that activation energy. And it does it by generating a different transition state. If we generate a different transition state, that different transition state can have a lower free energy, or lower the free energy of activation, and therefore increase the rate of the reaction. And this is what enzymes do. Enzymes bind to the substrate, they change the transition state of the reactants, and lower that free energy. That being said, if we go back and look at this, we only change this. What we do not change is where you start out here or where you end up here. We're not changing the products. We're not changing the reactants. Therefore, the one thing you do not change is this. We do not change this delta G between we're not changing the delta G between up here, the G of the reactants, and the G of the products. We're not changing that difference. So this delta G remains exactly the same. Therefore, enzymes do not alter the equilibrium. We are not altering the delta G. Okay. That's a few minutes early, but we're going to start talking about Michaelis-Menten kinetics now, and that's going to be kind of a big, another topic that's going to take more than the 4 remaining minutes that we have. So I am going to let you go now, and I will see you on, today is Wednesday, so next time will be Friday.